Refraction. For an incoming light ray, and we like to draw these parallel to the optical axis, when it hits the glass surface, it is being refracted, goes through the glass, hits the other surface and is refracted again. So overall we may get something like this, and I know this is going out of the picture, but that's okay. And then in astronomy, because objects are so far away, they're considered to be that their light rays are parallel, and that's why we're drawing these kind of parallel rays here. And again, it's being refracted, but because it hits the lens in a different place, it's perhaps not differently, or it's differently refracted and perhaps not as much. And so you see that these two are coming together. Usually the way we like to draw this is actually draw one here at the bottom. So here it hits, and again it's being refracted. Whoops. Turn this along just slightly. Oh, great. There we go. Just made a slight mistake and so if you can imagine that on the other side at some point they're going to come together, these three rays. And that's basically what refraction does, and that's also why we're using convex lenses, because the light needs to be bent towards the focal point of the lens so that we can actually produce an image on the other side. For reflection, well, if I draw a parallel ray here for a plane mirror, that of course will be reflected right back. So that's not telling us a whole lot. So I'm going to take these two away. So here, because I have a plane mirror here, which is not a telescope mirror, it's simply your wall mirror, I would use this one here. Whoops, didn't mean to do that one. I have the incoming ray, and then we have the outgoing ray, and what I'm doing here actually is I make sure that the incoming ray, that the angle of the incoming ray is the same as the angle of the outcoming ray. I believe you can see that the angle of incidence is the same as the angle of reflection, which is what the law of reflection says. It's the easiest law that there is. The angle is the same coming in as it's going out. Let me choose another kind of line, perhaps another color here. There we go. And perhaps have a steeper angle. There we go. And now I'm going to do the same thing. And there again, you have it going out. So coming in, going out, same angle, coming in, going out, same angle. However, this is not the mirror of a reflecting telescope. This was just to show that the angle of incidence is the same as the angle of reflection. So next I will do the reflecting telescope. Here we're back to the parallel rays, because when we teach optics, we always like to do that. Use these parallel rays. Again, far away objects, because stars and anything else in the universe is so far that their light rays can be considered to be parallel to each other. So here is one of them. I'll draw another one later. It hits the surface of the mirror, and now something important comes. The law of reflection applies. Even though the telescope mirror looks different, it's curved, but the law of reflection applies as follows. I'm going to choose what is called a tangent line, or the kind of, if you look at a small scale, you can interpret this part here as actually a plane mirror, and then again the law of reflection will apply for this part here. So if I do this right, then we get something like this here. And then I may use another one. Let's say I use a green one, and it hits the mirror in another part here. Notice it's closer to the middle of the mirror, and it's being reflected again with the law of reflection, keeping in mind that we have a little piece here that's actually straight, and the angle coming in is the same as the angle going out. And perhaps yet another ray. So again we have one coming in, and it's being reflected. And there we go. Oh, there's just really no point why I use different colors, just for contrast, I guess. So in a reflecting telescope, overall the law of reflection still applies.